You know what? It's the coolest subject in the world. People should know about it, and it should be taught in a way that's equally engaging for what it is. An equation that even the smartest person the smartest person arguably in the history of time was wrong about. Equation that he looked at and thought, no, this can't be real, and decades later, Nobel Prize winning scientists found out, oh, it actually is. An equation that could get your foot in the door on quantum mechanics and got my interest peaked when I started in the industry. An equation that is relevant to so much technology that we use today. You may have had whispers about quantum technology from some AI, crypto, finance, tech, bro hybrids that's just so smart and so not condescending at all. But here's the secret. 1, they probably don't know what they're talking about. 2, it's not as intimidating as they would want you to believe. So today we'll give you the fundamental of it in a way that I promise isn't going to dumb it down to the point it's irrelevant, and also is not going to be scary. We're going to hold hands the whole time. I wish there was someone else here so I could go, I'm gonna be holding your hand the whole time. Start with, why do we care? Why should we care? Why does this matter to us at all? And what are we talking about here? Well, the process is one word you may have heard of before: entanglement. This is a process that particles undergo. 2 particles, they combine to form one single state. To be specific, one single quantum state. This is known as entanglement. What does this look like? You put one box in London, one across the world in Tokyo. One, you know the inside is red, the other is blue. You open the one in London, you see the inside is red. This means you automatically know the one that in Tokyo is blue. The main property this emphasizes here is non-locality. Like, they aren't connected. There's no Bluetooth going on here. It's just intrinsically knowing if you open one box, the other box, no matter where it is, will be a different color, the opposite color. The objects aren't communicating anymore. They're just not really separated. Even though they could be as far as light years apart, they act as one. Okay, you think, obviously it's like a light switch. Weird, but aren't particles weird and mysterious in and of itself? Well, you're asking the right questions because you were being good company. A man who thought the same thing, Albert Einstein. In physics terms, we call this outcome being predetermined. It means when you open the box on one end, you know what the color is on the other. Open box, you see red in London, you know that Tokyo is then blue. However, even a genius, whether Einstein or you, is wrong sometimes. Experiments later came out, in fact in 2022, pretty recently, that shows before you open the box, there is no predetermined value. It's not that you open it and realize it was red. Before you open it, there was nothing there. Let me repeat. We thought, Einstein thought, okay, you open the box, you see red, you close the box, it must have been red the whole time. Therefore, when you open it and see the red, you know the one in Tokyo is blue. We get it, we've been over it a few times. However, what came out is before you open the box, there's no value. It's not red, it's not blue, it's actually a mysterious third thing that we don't know yet. Scientists describe this as being undetermined. Essentially, there could be a mysterious abyss. There could be the actual upside down. There could be the layer of Vecna itself in there. And we wouldn't know because once you open it, it selects an option. In fact, before the point of measurement, physicists don't fully understand what's going on here. They don't all agree on what's happening before we open the box. There are many theories, but what we do know is the experiments show that the inside of the box before we open it is not red. It is deeply, completely unknown, mysterious. We don't have an idea. It's just undetermined. It's question marks in the inside. It's not empty. It's not that there's nothing there. It's just that we don't know what it is. It's not red either. Anyway, enough about boxes. What does this mean about particles? What does this mean about things that we experience every single day? Well, you can have 2 particles any distance apart. We can say one in London, one in Tokyo. We can say one in London, one on the moon. We can say one in London, one across the universe itself. And once we know a property about one of them, we know a property about the entangled one. Scientists often choose a property called spin here. If one has spin up, the other will have spin down. Just like the example where one is the red box, the other is the blue box. Exact same thing, different property, now just applying to particles. And the rest of the analogy also applies. Before we measure them to see whether the spin is up or down, this then spin is unknown as well. It's in this mysterious state that we were talking about before where it's just unanswerable. But once we measure and we know one entangled particle is spin up, then we automatically know the other entangled particle will be spin down. That's right, that's right. It's not that hard, is it? It's not that scary. They all lied. Now to the money. Here's what you came for. Let's go to the equation. I know it looks scary. I know it looks like there's a lot of things here that aren't numbers. I know there's Greek as well. Ooh, intimidating. I promise you, just like the boxes that we had before, it's gonna be fine. We're gonna hold hands, we're gonna get through it together. This is representation of what we just talked about, an entangled pair of particles together, becoming one singular state. First, this. Psi, Greek letter, spelled P-S-I, pronounced psi, as in physicists label it with quantum states. Nothing deeper than that. As we talked about before, two particles become one single state, one single quantum state. This is that naming of the quantum state. Okay, cool. Here we have it. Greek letter, broken down, not scary anymore. Bracket symbols you're seeing, they're called ket vectors. Just means quantum state of. Think of it as a container. Whatever's inside these brackets describes what our system is doing currently. First section, 0, 1. 2 digits, 2 particles. 0, 1. Particle A is in the state 0, particle B is in the state 1. Remember that property spin that we talked about earlier? Well, let's say 0 is spin up, 1 is spin down. We have a representation for our system. Particle A is spin up, particle B is spin down. And then you can look at the other side and suddenly it's much more understandable. It's the opposite. So we have particle A in 1 and particle B in 0, which is spin down and then spin up. So we have our one system option here, our other system option here. Now, what's curious to look at is the plus in the middle. Plus sign means before we open the red box, before we know what the particle measurement system is, it's not one or the other. It's a configuration of both of them. This is what we call superposition. It's our evidence that entanglement has happened. It means until you measure it, both possibilities exist simultaneously. Finally, we have the pesky root 2. It's not scary, it's something called normalization. At this point, cut it, you don't need to know what it means. It just means that we're scaling the probability. So in a system where you have 100% chance of one of these outcomes happening, this root 2 means that you either have 50% chance of outcome 1, 50% chance of outcome 2. Going back to the box, you have 50% chance of it being red, 50% chance of it being blue. That's it. Again, not scary. Going over it all together, the system we have in place, the option 1 is you can have particle A spin up, particle B we automatically know is spin down. Or you can have particle A spin down, particle B spin up. And the chance of either one happening is exactly 50%. Before you measure them, you don't know. It's 50-50 either way. After you measure it, you can see which one it is, and it's 100% one of the ways. This is the equation. You're now as smart as Einstein. In fact, you're probably smarter than those crypto guys we talked about. We just did some pretty intense maths, so let's take 5, take a breather, and let's take some calls. What does the advice line say?
Oh, how do particles get entangled in the first place?
It's hard for particles to become entangled. You need very specific lab conditions. Specific interactions like firing lasers through crystals at these particles then produce entangled photon, which are light particle pairs. It's not a random process. It's not something that happens casually in nature at scale.
How far apart do they have to be?
There's no known limit of distance. The record is over 1,200 kilometers in China, found by a satellite experiment in 2017. In principle, could be across the universe. Distance never weakens it.
Oh, my friend and her boyfriend are really spiritually linked, like she's always saying.
Technically, hypothetically, every particle that's ever interacted with another particle could be entangled. Entanglement is fragile. It breaks when particles interact with something else in a process known as decoherence. Your physical body is trillions with a T particles interacting with each other and the environment around you. So perhaps for a second, I don't even want to say that. I don't want to say perhaps. That's not true. The truth is, any entanglement between two people would decohere within a second the minute you leave. What you're feeling is an insecure attachment style. It's not entanglement, babes. Also, let's be real here. Does your boyfriend have the energy that you could sense it across worlds? Do you really think a man could do that for you? Remember why this is relevant to our everyday lives? In 2022, there are 3 scientists, Aspect, Clauser, Ziegler, Rachel? Aspect, Clauser, Zellinger, won the Nobel Prize in Physics, proving entanglement is real and that Einstein's hidden variables, the predetermined outcomes for the box, don't exist. Right now, big names in tech, IBM, Google, are using entanglement as the basis for research in their quantum processor. China has built a quantum communication network based on entanglement that is theoretically impossible to hack because of the way these particles combine together. And researchers every single year are pushing the limits to what entanglement distance can be. today you've done so much. You've learned about what entanglement was, why Einstein was wrong, the equation that proved him wrong, the technology it relies on today, and the basis for all future quantum mechanics and quantum physics. How exciting! What a nice place to be in. And I've always thought about it this way. It's the coolest subject in the world. It deserves to be treated like that. It deserves to be taught like that. So I will see you again and again and again to teach you more and more and more. Thank you so much for watching. Somewhere on the screen will be my latest video. I hope we only go upwards from here. It took a lot to get this out, and I hope it was valuable. I hope it keeps being valuable. I'm really happy to be here.